let's try to solve this problem over here. So you are given a force extension graph over here, which is F and your delta L over here, and you have two wire P and wire Q. Wire P experienced a maximum force of 50 Newton, and by that time, it experienced an extension of 3 mm. Whereas for wire Q, it experienced a maximum force of 30 Newton, and at the end of it, you see that the extension that happens to wire Q is the same as wire P, which is 3 mm as well. Okay, so the figure above shows the force extension graph of two wires P and Q of the same material. You see the words of the same material, that means by if they have the same material, what would be the same? They will have the same Young's modulus. Why is it so? Because Young's modulus only depends on the material you use only. Okay, so this here means that you have the same Y. Okay, because Young's modulus depends on the type of material only. Okay, Young's modulus depends on type of materials only. It doesn't depend on how you shape the material. Okay, if you want to shape it into a donut shape, you want to shape it into a sphere, you want to shape it into a pyramid, you want to shape it into a cylinder, no matter what kind of shape is it, if it's the same type of material, the Young's modulus will still be the same. Okay, so we say Young's modulus of copper is what? And then that value is valid even though the copper is shaped into a donut, a circle, a sphere, or a ring, a plate, you still have the same Young's modulus because Young's modulus depends on material. Okay? Both the wires have the same length. Okay, so now you know that the Young's modulus of P is the same as the Young's modulus of Q. Then after that, from this particular statement over here, same length, you know that the length of the P, original length maybe, okay, original length makes more sense. The original length of P is the same as the original length of Q. Okay, then they are both 1.5 meter. Then they have different diameter. If you see the word different diameter, what does it imply? It implies that you have different cross-sectional area. So the cross-sectional area of P will not be the same as the cross-sectional area of Q, because you know the area is pi r square. R, the radius, is just half of diameter. So if they have different diameter, they have different radius. If they have different radius, they have different cross-sectional area. So these two P and Q wire, they are not supposed to have the same cross-sectional area. Okay, then they tell you that the diameter of wire P is 0.58 millimeter. Okay, so this is an extra information for the diameter of wire P. So now they ask you to determine the diameter of wire Q. Okay, many ways to do this. Okay, let's try it out. Okay, there's many ways. You have two wire over here, so you can think of it as a ratio problem. So ratio problem, we can go through the same 3 steps. Okay, so the first step would be to determine the relationship between the manipulated variable and the responding variable. What's the relationship between the manipulated? What are we manipulating? Okay, diameter, right? Okay, we are manipulating the diameter, then as a result, they experience different force and different extension. Okay, you are manipulating the diameter. As a result, you are changing the force experience and also the extension. So we want an equation that relates between the diameter, the force, and also the extension. Well, I think you can see it again. It's the Young's modulus equation, because force can be related, force and area form stress. Again, area is related to the diameter, force and area form stress. Change of length and original length, which is given 1.5 meter over here, they form strain. Stress and strain related together by Young's modulus. So again, the equation will be y is equals to force divided by area, change of length divided by the original length. But we can probably shift the things that we are interested to the left hand side. Okay, the thing we are interested to is the diameter, because diameter is what we manipulate. So we can probably expand the area. The area is pi r square, right? So the area, pi r square, r is just half of the diameter. So we can expand it this way. Pi half of diameter, which is r, pi r square. Okay, divide by the change of length, divide by L naught. So this is the equation for Young's modulus. Now we wish to shift the diameter to the left hand side. Okay, now this can be a bit complicated because I'm doing a different way. Let me do it slow, okay. Whether I choose to do this way, I'm not sure, but never mind, let's proceed through it. If you bring it to the other side, then it will be y multiplied by delta L divided by L naught will be F pi d over 2 square. So d over 2 square. Why to do it? F y delta L pi down there, then square root, then multiply by 2. Okay, so write it again. The diameter is equals to square root of F L naught pi y delta L multiplied by 2. Okay, so this is the equation for diameter. You already determined it. Now you find the relationship between old and new. Second step. Okay, you know that for force, the force experienced by P is 50 Newton, whereas the force experienced by Q it's 30 Newton. What else do you know? How about the original length? The original length of P is the same as the original length of Q, which is equals to 1.5 meter. Pi, no need to think about it. The Young's modulus of P is the same as the Young's modulus of Q, which you are not sure what's the value. And lastly, the extension that happens to P is the same as the extension that happens to Q, which if you look over here, they have the same extension, which is 3 millimeter. So write in meter, 3 times 10 to the power negative 3 meter. Okay, so you determine all the relationship you need already. The last step here, okay, our space, I write it here, is to take the new equation, divide by the old equation. Let's call, it's not necessarily new divided by old, and it's over here I call it old and new. It's because we usually have an old situation, then we change it, then we have a new situation. But here we don't have a before and after situation. What we have here, it's just P and Q lah. Okay, so let's change it out. My mistake. So this is P, this is Q. Okay, so now we are not going to take P divided by Q. We are not going to take new divided by old. What are we going to do is we are going to take Q divided by P. Okay, take one situation divided by another situation. So you have your D of Q, which is equals to 2 times square root force experienced by Q, length of Q, pi y of Q, delta L of Q, divide by diameter of P, which is 2 times of force experienced by P, original length of P, pi y of P, change of length of P. For now, we can cross out what are equal. So our equals are the original length and the extension. They are the same. So original length can cross out, extension can cross out. Then we also know that they have the same Young's modulus, so that can cross out as well. Then you know pi is the same value. So now you are left with this equation, or 2 can also cross out, of course. So now you have square root of FQ divided by square root of FP. And you can combine the square root together. Then right now FQ is just, what is FQ? FQ is 30. Then FP is 50. Again, this is dq over dp. Yeah. So from here, you can find the ratio to be 3 over 5 dq, then dp over here. Okay, you already have the diameter of wire P, which is 0.58. mm, change it to meter. So now if you put it inside your calculator, I believe you get an answer of 0.45 times 10 to the power of negative 3 meter. Okay, let me do a quick double check. Yes, okay. So this will be your diameter of wire Q. Okay, so I'm doing this question using the standard ratio problem ways of doing things. Find the relationship between the manipulated variable, which is diameter, and the responding variable, which is the other things related to Young's modulus. So use the Young's modulus equation, you rearrange so that your subject move to the left, the rest on the right. Okay, then you find for all these things inside, you find the relationship between P and Q. If you have a relationship, they're equal, you can say they're equal. If they're not equal, what are their value? You list it down first. Then you take Q divided by P. If you want to take P divided by Q, also both are fine as well. You just need to make sure what are the same so that you can cross them out. What are different should remain. Then you can substitute in your value, and from there you can determine what you need to determine. Okay, so it's a standard ratio problem. I hope you are clear how to use these 3 steps to solve the problem here. Okay, so that's it for this question. Thank you very much.